M-A-T-T-E-R. So what is matter composed of? Elements. Can we create matter? Yes. Can we destroy matter? Yes, but it doesn't disappear. Matter exists in one form or the other. Okay, whatever disappears, like energy, can be converted from one to another, and we come from atoms, we grow up to be organisms, and when organisms die, they go back to become elements, whichever way the body is processed. Okay, so elements, you have more than 100 plus elements. There's the International Union of Chemistry that approves these elements to be listed. So some of them are obvious for us, like carbon, hydrogen, oxygen, nitrogen, and so on. So these are all individual elements. It's a long list. But carbon, hydrogen, oxygen, and nitrogen, they are considered to be major elements, and there are some more that are more relevant to biology or biological organisms. So you have all the numbers there. If you see under the chemical elements heading, you can see how many elements and what percent is what. So that's all for your information. Okay, but you need to know which are the major elements that we need to make all the biomolecules, mainly carbon, hydrogen, oxygen, nitrogen, besides a few other elements that we will be later on talking about: sodium, potassium, calcium. Some of the elements the body needs in large amounts, some of them you need in small amounts. When you require some elements in small amounts, they are called trace elements, or sometimes they use the term minor elements. And the major elements are the ones that we need in large amounts. When you see minerals come from the soil, like rocks and soil formation. So some of them are extracted from the soil, they consider them as minerals. And you can see on table 2.1 which are considered major elements, minor or lesser elements, and then trace elements. So compared to one, you need this in lesser amounts on a daily basis, on an average, and this you need very, very minute quantities. So you find carbon, oxygen, hydrogen, nitrogen, calcium, phosphorus under major elements, and the lesser elements you have sulfur, potassium, sodium, chlorine, magnesium, iron, and the rest are considered as trace elements as percentage of body weight. So do we have to memorize this? No. Do we have to know the numbers? No. What do we have to know? The meaning, which one could be what?
All of those?
Yeah, you should be able to tell whether my oxygen is do I need a lot of oxygen or less of oxygen? You need to be able to tell whether you need more of copper on a daily basis. Your body needs a lot of copper or less amount of copper, right? So you have to, when you read through that, you will get an idea. So you have to do, see, this is just the beginning. You have a lot of memorization to do. This is not just one. Okay, so when you have to remember such a table, you have to do an elimination process if you cannot just keep that in mind. Okay, so like the important ones are the major elements, right? So if you know at least those, then you can know that the others they don't belong to that category, right? So you're doing an elimination process. I'm just giving you an idea how you can retain some table. You don't want to, I'm saying you don't have to memorize those numbers, but honestly, all these tables and numbers at some point you have to know by heart if you are going to get into your programs, because in those tests they are not going to give you any room. Okay, they expect you to know all numbers and all names, everything, whether it's nursing entrance exam or pharmacy entrance exam, whichever. So this is just a beginning. If you don't want to invest the time now to learn some of these things, I don't know when you will do it, the day before that exam, no way, right? So you will be asking me this question always, so I'm going to leave it to you. I do expect you to know some basics for any table or any figure, but I don't want, certain times I want you to memorize the numbers, I will emphasize, okay? But at least the elements we should know at this point. So each element has a certain structure, yeah?
You mean major in all of them,
Yes,
basically?
all of them.
All right.
Okay. My answer will be always all.
All right.
So don't even ask. I'll try to be as fair as possible, but you have to try.
All right.
If you leave it, then I won't leave it. So if you take any one of those elements, you can see here the long list. Let's look at some of them. Oxygen, carbon, for example, or nitrogen. You see in the box, what do we see? We see two numbers. Carbon, 6 and 12 something, right? So this is based on what they call the atom. The atom has protons and neutrons. Protons represented by small p, those are positively charged. You can see that in that figure at the bottom of the same page. They have given 4 examples. Okay, so in the middle, what we call the nucleus, the center, you have protons and neutrons. Neutrons don't have charge. So how do I remember? P for proton, P for positive. N for neutron, N for neutral, no charge. Okay, what about the electrons? They are on the outside. Depending on the atom, you will see so many number of electrons. Okay, in this case, carbon will have 6 protons, 6 neutrons, and 6 electrons. So normally atoms are balanced in terms of their protons, neutrons, and electrons. Okay, so which means 6 positive charges, 6 negative charges on the shells outside. So the net charge is, there's no charge normally. Okay, atoms have balanced number of protons, neutrons, and electrons. So the number here represents atomic number, which is basically the number of protons. How many protons we have here? 6. And what do we have here is the bottom number is the atomic mass. Sometimes they say weight, but mass is preferable. And this is number of P plus number of N, meaning number of protons plus number of neutrons, which gives you the 12. But you don't have a whole number 12, you have a fraction. We'll talk about that later. So I want you to quickly go through those elements that they have listed in figure 2.1 and see if you can understand what they are trying to say there. Each one, they have listed the atomic number, atomic mass. For carbon, nitrogen, sodium, potassium. So the table tells you how many protons are there, the top number. And you know normally everything is balanced. So if you have so many of these, so many of those, right? P's, N's, and E's, they are all equal. Protons, neutrons, electrons, right? So if you take any element for that matter, so if you take chromium, 24 what? Protons, which is atomic number.
And the
51 is atomic mass,
Mass.
which is the protons plus neutrons. But the number is not exactly double. There's a reason for that. Those of you who know what isotopes are, isotopes or alternative forms of the same element which have more number of neutrons than normal. Okay, carbon has, instead of 6 plus 6, let us say 6 plus 7 and 6 plus 8. One carbon has 13 atomic mass, another one has 14, and one has 12, then they average. I'm just giving you an example, it's not the exact number for the isotope. So that's why you see all fractions here. They take an average number and put it there for all the different forms. So it may not be always exactly the double. But basically, by definition, this works because it's number of protons plus number of neutrons.
What's underneath mass? Divided by
Weight. We use mass because mass will not vary, the weight will vary. Like if you are here or up in space, you weigh different. But the mass will not vary whether you are here or in zero gravity. So that's why it's good to use atomic mass and atomic weight.
And how do you know the weight? How do you know the
It's the same thing. It's the same thing, but the weight varies.
What?
Atomic mass and atomic weight are the same thing. Mass is the volume of the substance. Okay, not exactly the volume, the amount of the substance, how much you have in your body. But the weight is measured in terms of pounds or kilograms, and that will vary depending on the effect of gravity. Okay, but we can get more into that. I don't have the time to get into the details, but we can talk about that if you need later on. So some of these basic things, that's where it helps. If you do some YouTubing or Googling, some of these things, you make a note where you have a confusion, or you can talk to me after class, I can explain that. We have a lot of things to cover in this 1 hour. I don't mean to cut you off, but we have to cover some
No, I
of
just
them.
wanted quick answers.
Yeah, so that doesn't make it clear for you, I know, whatever I
I have
answered.
an idea.
Yeah, good, that helps. I appreciate questions, but I can keep it short, but if I need to explain more, we can do it after my lecture. So the next item you have, you see on page 45, valence electrons. The electrons are arranged in an order in the shells outside depending on the number of electrons you have. There is a formula that you can use. Two n to the power 2. The n represents the shell number 1, shell number 2, and so on. So how many maximum it can hold? So if you put number 1 for the shell number 1, that gives you a value 2. So you can have only 2. Then the next one, you can have up to 8 electrons. And the third one, you can have up to 18, and so on. Okay, this is the easy way. If you are taking a chemistry class, we are not going to go that far. But if you wonder how do I place my electrons, that's how you do it. Okay. So most of the elements we deal with for biological sciences, they are within the 3 to 4 shell range, not beyond that. Okay. So if you have carbon, 6 protons, meaning everything is 6, so you have 6 electrons. You put the first 2 in shell number 1, and the remaining up to 8 goes in the next shell. But you have only 4 left, right? You put the 2 in the first shell, and the next 4 goes in the next. But if you had some element like, let's say, chromium with 24, so then you'll have 24p, 24n, and on the outside you have to put 24, you'll put the first 2 in the first shell, then you'll put 8, so it will be 2, 8, 18, but you have only 24, right? 2 plus 10, 8, 2 plus 8 is 10, so you have only 14. That goes in the third shell. You get some idea? So that's what they have represented there in that figure 2-1. So you need to know the atomic number, and then you can understand what those figures represent. So these electrons in the shells on the outside, the outermost shell, depending on how many shells an element has, they call them valence electrons. It could be 1 or it could be 8. So what the atoms tend to do, irrespective of the number of shells, always they try to maintain 8 electrons in the outermost orbit or the shell by nature. Okay, so when it is not 8, let's say one has like 6 and another element has like 2, the tendency of these atoms is either this would like to grab these 2 or this would go there. But it's easier to grab 2 than pull all the 6 over here. So this will tend to lose these electrons and they will jump over here. So when they do that, what is getting disturbed? Your charge balance. Normally they're balanced, right? Your positives and negatives are balanced. So when the electrons start jumping between atoms, they become charged. Then we call them ions. Okay, atoms are charged, then they become ions. So what are ions? Ions are charged atoms. They could be either positively charged or negatively charged. We will see that in the following page, but let's look at the isotopes. I did make a mention. Isotopes are alternate forms of elements with a different number of neutrons. Everything is the same as the original element, but it's in another form with more or less neutrons. And some of them are called radioisotopes, and they emit radioactivity. Because when you have anything that's not normal in terms of the atomic mass, because of the excess or less of neutrons, they tend to come back to that normal number. So when they do that, some isotopes emit radioactivity. Those are the radioisotopes. Then you see the physical half-life, ionizing radiation. So when you have radioactivity, they emit certain radiations that will disturb some of the elements. So they will convert them into ions, which will be more reactive. So they call them ionizing radiation. And the physical half-life is when these isotopes are not stable, they tend to come back to the normal stable configuration. And that time they reduce physically their atomic mass by getting rid of the neutrons. So then they call it the physical half-life. How long it takes for certain isotopes to reduce physically to half the amount. That's physical half-life. And then in the next page, if you see, it talks about biological half-life. Biological half-life relates to radioisotopes that are radioactive. So there is, let's say, 100% radioactivity. So how long it takes for a radioisotope that emits radioactivity to come to 50% of that original level? It could be a few hours, few days, few weeks, few months, or years, depending on the element. So you should know the difference between physical half-life and biological half-life. Physical half-life is that radioactive material to degrade and physically lose the amount, become half. But biological half-life relates to the radioactivity, to reduce from whatever the original radioactivity to half of the original radioactivity. Then you have ions, electrolytes. Just now I talked about the ions. Ions are nothing but the atoms that have lost or gained some electrons. You have an example on the following page, 47, figure 2.4. I want you to take a minute and look at that. They have given a sodium atom and a chlorine atom and what is happening in steps 1 and 2. You want, you can look up the sodium and chlorine on the chart if you need that information, where that atomic number comes from, why do we need that. So take a minute or two, then we will talk about that. So what is the atomic number for sodium? 11. And the atomic mass? So you have 11 protons, neutrons, so 22 is the atomic mass, and the electrons are 11, right? So if you have to put it in the shells, how will you do that? Using that formula, you can put 2, 8, 18, and so on. So you'll put 2, next cell 8, and you have 1. That's what you have for sodium, right?
Mm-hmm.
What is the chlorine? What is the atomic number? Where is chlorine? 17. Okay. So you have 2, 8, and 7. Okay. So you have 7 electrons in the outermost orbit. Here you have 1 electron. Okay. So now everything is fine, but the atoms don't want to stay alone, like we don't want to stay alone. Maybe some of us, okay, everybody needs some company. So these atoms tend to stay with someone else, okay? So the easiest way is for one person to go there and bring all these 7 guys over here, right? So look at the next picture or see those arrows. So 1 electron jumps to the other, right? So when you do that, so the original sodium had a net 0 charge. Now you lost 1 electron, so the overall charge became positive. And the other one gained a negative charge. It became negative. So now they have become ions. There are no more atoms. They are the same atoms, but they have become charged. Now they call them. So whenever you see any symbol written like this, that means it's an ion, sodium ion or chloride ion, and it's positively or negatively charged.
How is that jump actually initiated? Just by coming close?
Yeah, the atoms always, they keep on colliding with each other. Even all the air, whatever molecules we don't get to see, they're all moving around and bumping into each other. Even in anything, even if you see, there is movement within that. But don't ask me how and why, because I'm not an expert on that. But it is proven that all matter, everything inside, they are moving in a very close range that you don't see it. Okay, so because of the random, like when you start the Microsoft Windows, what do you see? The 4 dots bump into each other and they get a logo, right? They give you a logo, something like that. Can you imagine that and relate to this?
So, like if you have, say, a solution with sodium chloride in it, is there going to be some sodium chloride and then just floating?
Exactly, depending on the concentration. Okay. So the salt, when you put in water, it disappears because the bonds are broken and those ions are kept away from each other by the water, so you don't see the salt. But if you evaporate, you see the salt. Why? Your water is remote, nobody keeping those guys apart, so down there together. Okay? That's a simple way to explain. So ions are electrically charged atoms, and because of this difference in charge, they attract each other, so they tend to stay closer. So this kind of attraction they call ionic bonding. There are different ways of bonding between atoms to make more complex molecules. say carbon and oxygen can form carbon monoxide, or carbon 2 oxygens can form carbon dioxide, hydrogen and oxygen can form water, and so on. Sodium and chlorine can form sodium chloride. Okay. Electrolytes. What are electrolytes? Electrolytes are substances that dissolve in water and they become ions and they are able to conduct electricity. How does electricity form? You have a positive and negative, right? In a battery or anything. The same way, when you have positive and negative ions, they tend to conduct electricity. So those are called electrolytes. Sodium chloride is an example. When you put in water, it dissociates into ions, and that can conduct electricity. So those are electrolytes, substances that ionize in water and form solutions capable of conducting electricity. Free radicals have odd number of electrons that don't fit with the standard configuration. Okay. So normally we don't have that, but sometimes we do. That's where all the, what do you eat? You're asked to eat certain things to prevent damage from free radicals, right? I forgot the name. Antioxidants. There you go. So in table 2.2 you see some examples for electrolytes that will dissociate and conduct electricity. Calcium chloride, magnesium chloride, potassium chloride, and so on. Yeah, antioxidant is on the next page. That neutralizes the effect of free radicals. Okay, moving on, molecules and compounds. Atoms come together to form what we call molecules. Okay? Molecules need not be compounds. Can anybody tell if you read or if you understood what is the difference between a compound and a molecule?
Oh. No, I didn't.
Just say it.
No, I
problem.
was thinking the DNA, the RNA, and the fats and the proteins make macromolecules, right?
Yeah, they are macromolecules, you're correct. But I was trying to see the difference between what is a molecule, what is a compound. Somebody there, 1 second.
The type of bonding,
Okay,
like covalent ion.
okay, I'll come to that.
A compound has two elements and a molecule can have...
Two different elements, okay? The bonding is essential to make those molecules and compounds, but molecules are just more than one element of the same kind. Like hydrogen, you have hydrogen and hydrogen. Nitrogen, you have like 3 nitrogens together. Or oxygen molecule exists as 2. So these are simply molecules. So how are they different from the compounds? What is the difference you see here and there? They are made up of more than one completely different element. They are not the same. So anything is a molecule, but to qualify as a compound, it has to have more than one kind of element. See, carbon, oxygen, or hydrogen, oxygen, sodium, chloride, potassium, chloride, right? So you should know the difference between molecules and compounds.
Well, quick question. Just because it says in the book that the molecules could either be of the same,
Or
like
different.
nitrogen, or different. So is that
Yeah,
the difference?
yeah,
Like,
because
either or.
These are also molecules,
Oh,
but these
okay.
are not compounds.
Okay.
Compounds are molecules, but molecules, all molecules need not be compounds, right? So to make it simple, all are molecules. Okay? If it is a compound, you will find different elements. If it is the same, so there are very few that fall in this category, okay? Most of them we encounter are compounds. Mix more than one type of element. Then you have isomers. What are isomers? Isomers have the same formula, but the arrangement of the atoms are different. The arrangement of the individual atoms, like if you take glucose, it is C2H12O6, but there are different variations of the same glucose. Okay, those are called isomers. So different ways you can arrange those carbons, hydrogens, and oxygens. And molecular weight, how do you find the molecular weight or molecular mass for H2O, water? How many atoms of hydrogen we have? Oxygen.
One.
So what's the atomic mass for hydrogen over there?
One.
1 point something, let's say 1. So it will be what? 2 times 1. What about oxygen? 15.9, let's say 16. So it will be 18. 18 is your molecular weight, 1 molecule of water. So the same thing, if it is 3 molecules of water, what will you do? 3 times, right? What about glucose? What's the atomic mass for carbon? 12, right? So how many carbons? 6 times 12. What about hydrogen? 1, right? How many hydrogens? So 12 times 1 is 12. Oxygen, we just did, right? 16 times how many oxygens? 96. So what is the total?
80.
This is the 180 is the molecular weight for glucose. So like that, for anything you can calculate, you know the formula for it. So you don't have to know the formula, but you have to understand what is molecular weight, how you get that, right?
Can you do one more example, please?
Give me the name of a compound.
That same one.
What's the same one?
That one right there.
Water.
Can you show me how you
Let's
got the
do,
number? Can you show me how you got the number?
this one. This is
All
a
the
fixed
numbers.
formula. H2O gives you water.
Mhm.
Okay, so we already talked about the atomic mass and how do we get that from this table. Somebody did all the work and they put it in the table for us. So if you don't memorize the table we refer to the table. Okay, and you see the atomic number here, atomic mass here, right? So for hydrogen it's 1. Oxygen we rounded off to 16, right?
Right.
Because it's more than anything more than
Oh,
0.5
right.
you can
Oh.
make round off. If it's less than, just for calculation purpose, that's how they do it. You can do exactly also, you can still round off or keep it, but normally we round off if it's more than 5, okay? So you have only 1 oxygen, we don't write 1, so you put 16, you have 2 hydrogens, so 2 multiplied by 1 is 2, right?
Right.
The atomic mass is 1 on the table, on the bottom.
Yeah, but how come we're looking at the top number on one and the bottom on the other?
Because this is your atomic number, this is your atomic mass, we did that already. This is the number of protons, this is the number of protons plus neutrons. So this is given, this is a convention, this is a rule. So always when you have to look at the weight or mass, you have to look at the bottom number, whichever the element. But if you want to know how many protons, electrons, neutrons are there, you have to look at this and also you can look at this, but ideally this, because this number is always not double because of the isotopes. Okay, so if you have to count the numbers of each one, you have to look at this number. This tells you have 35 protons, 35 neutrons, 35 electrons. But if you have to count the weight, then you have to look at this number. That's the weight of this particular atom. And depending on what is present, you just multiply and add depending on the numbers. Okay? That's for now, but we can talk more. Okay, so in order for these elements to collide, hit each other, grab these electrons and make those bonds, they need energy. And also, there are different types of bonds. One is the ionic bonds based on the jumping of the electron. I won't say jumping, I would say transfer of electrons between atoms that gives them or makes them charged ions. So based on ion formation, you have the ionic bonding. But there are situations, as you can see in figure 2.6, page 49, what is happening there? They are not transferred. They are being shared. The electrons between two atoms, it could be hydrogen, hydrogen, or one carbon and two oxygens. They are sharing the electrons. They are pairs of electrons. Okay, so you can see one oxygen, hydrogen has only one, so it cannot get rid of it. So they can only come together. That's why you have H2. I think I wrote here H and H, right? So they are sharing whatever they have. But if you take the other one, you are sharing two pairs of electrons from one side and two from the other. And this kind of sharing leads to formation of what they call covalent bonds. So depending on number of electrons that are being shared between two atoms in the outermost shell, if you have only one pair or two pair or three pairs, they normally denote by, you have an oxygen here, a carbon here, and you are sharing two pairs of electrons on either side. So they denote by these two lines. So they call it double bond. In some cases you will have only one, okay, hydrogen and hydrogen, only one bond, one pair of electrons being shared. In this case, the second figure, you have two pairs of electrons being shared, or it could be more depending on the case. So you may find 1, 2, 3 in most cases. Some you'll find 1, some you'll find 2. This represents how many pairs of electrons are being shared between atoms. These come under the category of covalent bondings, and these are the strongest. Okay, covalent bonds based on sharing of electrons. Ionic bonds based on attraction between charges, the positive and negative between the ions. And then the third category of bonds, hydrogen bonds. Hydrogens are involved in certain type of bond formation. That's the weakest. They easily break off. Hydrogen bonds involve hydrogen. So the strongest. Next. Why do we need to know this? A lot of your biomolecules, like your enzymes or hormones or some of those major molecules, they have to be stable most of the time. They cannot break apart. Then your system is not going to function right. So they all primarily use covalent bonds. There may be other bonds in that macromolecule, but mostly covalent bonds. Wherever you have to have reactions, okay, you will find ionic bonds. Wherever some structures like your DNA, you are talking about DNA, it's a structure with the two strands. The cells keep on multiplying, or cells make proteins, you need to open and close the DNA strand constantly. In those cases, you will find hydrogen bonds between the two strands. Okay, so depending on the needs, you will find the different types of bonds. And then there's one last category, that's the van der Waals forces at the end of the page. That's some unexplained attraction between atoms which don't fit into these categories. There is some residual charge which has nothing to do with your electron balancing and all. That's called van der Waals forces. Random, brief attractions between neutral atoms, even when there is no charge. So 4 types of bonding. Right? Next, we will talk about water. I'll give you a couple of minutes if you want to look up those figures. And they have a table where they have compared those different bonds. Then we will talk about water and pH. Yeah.
Could you maybe draw
What did he
a
say this
compound
represents?
that has hydrogen molecules?
Like
Um,
it's like when
You
the
can see figure 2.8, you have it right there, page 50,
when
between
like this,
two
right,
water
when they
molecules, okay?
when they have multiple
You have water, hydrogen and oxygen, and a
multiple
neighboring
connection or something
hydrogen.
that's connected. That's connected right, to the other molecule.
H2.
I don't know exactly what I call.
So you can see the hydrogen has a little bit of positive charge and the oxygen has a little bit of negative charge, and there is attraction always between them. And these attractions are transient or temporary, so they are not very strong. So they tend to stay. So the water molecules, when you put water, it spreads like a sheet on the table or wherever you spill. They take the shape of whatever the container is because of that property. Okay, they have a little bit of tendency to stick together, the water molecules. So that's why they call those hydrogen bonds. We need a book, by the way, because I wouldn't have the time to draw everything every time we have a question. So everything is in the book. If you don't have a book, it's not going to work. Going to figure 2.9, what do we see there? What do we have in the middle? Sodium and chloride. So this is like two guys who want to come together, and this water is getting in between like a flood separating two guys. You have the water separating the sodium and chloride, right? How is this happening? Because your sodium chloride, when you put in water, you don't see it when you mix, right? Because of this. So all the oxygen in the water that surrounds all the negative charges, the red one, you see the red color, so it surrounds the sodium and keeps it away. So the sodium is attracted to the negative of the water molecule, negative charge on the oxygen. And in the other way around, look at the chloride. It's surrounded by the blue dots, right? Because those are having a little positive charge. So they surround the negative chloride ion, so they are separate forever, unless you remove the water. So how do you remove the water? If you boil, if you evaporate, then you'll see the salt at the bottom. Okay? So this is one example, but there are many situations where these things keep happening constantly. So as you read more and more into the physiology of different systems, that's when this basis helps. Otherwise, you'll be blinking at what is going on. So if you have a background information about all of this, then you will understand the physiology better. Otherwise, you'll be just memorizing everything. Okay? Moving on, solutions, colloids, suspensions. So when you make certain mixtures, you get all kinds of mixtures. Some they call solutions, some you call colloids, some you call solutions. So if you see that figure 210, you see the tubes. Okay. What is a solution? Solution consists of particles that are homogeneously mixed or thoroughly mixed. You have two things when you make a solution. One we call solute, one we call solvent. Solute is the substance you dissolve in something. So if you are making coffee in the morning or Gatorade, the powder you dissolve, that's called the solute. It could be any chemical, anything in the form of a powder. It could be a gas and gas mixture. You can make all kinds of mixtures. Usually solutions refer to liquid in liquid or solid in liquid. You can dilute orange juice, concentrate, or you can make a Gatorade solution, right? So when you do that, if it completely dissolves, the solute dissolves in the solvent, then it's called a solution. It will be thoroughly mixed and it will be clear. the solution. So you can look at figure A, 210, the first tube, right? That's an example for a solution. So you need to know what is solute, solvent, what is solution. Solute is usually in smaller amount compared to the solvent. You don't put 1 pound of Gatorade in 10 ml of water, do you? No, the other way around. You put 10 grams in 1 liter maybe. Colloids, the next. What is the difference between solution and colloid? So colloid is the same as a solution, but it's not clear. When you mix, it looks cloudy. So usually if you have any proteins in solution in water or some other solvent, it looks cloudy. You cannot see through, as you see in the picture. So colloids, cloudy. Sounds similar, right? Colloid, cloudy. If you want to remember, cloudy appearance is typical for colloids. And then the next, you have suspension. Suspension, no mixing between the two things, the solute and solvent. So what could be an easy example? Think of oil and water, right? You put fat, oil in water, it's not going to mix. They'll stand separate. Those are suspensions. So you can have like some small particles like sand. If you mix in water, you can see the dirt, the sand particles suspended. But if you leave it, it will settle down after some time. But if you add oil and water, one is hydrophobic, one is hydrophilic, so they never mix, they stand separate. Then you have measures of concentration. How do you measure things? You can measure things weight over volume. You can take something, so many grams of something, and dissolve in so many liters or milliliters, that is weight over volume. Percentages, whenever you talk about percentage, we are talking about 1 part in how many parts? 100, that's percentage, okay? Don't say I don't know that, please. Molarity. What is molarity? This is where the molecular weight comes handy. We learned about molecular weight, right? What is the molecular weight or molecular mass? What is that? We just did that. We did some examples.
The weight of all the
All the atoms present in that compound, exactly. Okay, the total, basically the weight of the molecule, one molecule of something. So 1 molecule of glucose or sodium chloride or whatever. So if you take that much grams of that substance, so for glucose how much we had? 180, right? So if you take 1 molecular weight of any substance and dissolve in 1 liter of water, that gives you 1 molar solution. Okay, so what molarity tells us that how many moles of that substance is present in a given solution. So if you have a 1 molar solution, you will have 1 molecule, let's say 1 molar glucose. Okay, so you will have 180 grams in 1 liter, that is 1 molar. You can make 2 molars by doubling the quantity of glucose or reducing the quantity of water, or you can make half a molar, 0.1 molar, all these variations. That's simple math. But by definition, 1 molar means 1 molecular weight of any given substance in 1 liter of water. And they have given some examples for you to read. So some of these, for some of you, it may be new, so you need to go back and review it, because maybe you didn't understand when you read it, but you can understand hopefully after I have explained. So molarity, the definition is on the following page, 54. Exactly what I mentioned, and they have given the same example. Can you see that? Then look at figure 211, okay? What do we see there? On the top, you see 5% glucose and then 5% sucrose, okay? So you have 5% glucose, meaning 5 grams in 100 milliliters or 50 grams in 1 liter. okay? And 5% sucrose is the same, but it's a different substance.